Musk's electric vehicle bet. You remember when electric cars felt like a joke. They were slow, had tiny range, and charging seemed like a fairy tale. The Tesla founder bet everything that could change. He pushed cars that felt fast and desirable, and then forced an entire supply chain to catch up. Here is what happened. The early model cars were proof of concept. Then batteries got better and cheaper. Now, manufacturers use new chemistries and faster manufacturing to drive costs down. Charging stations went from rare curiosities to fast chargers that can add a useful amount of range in under 20 minutes. Some networks now promise 80% charge in a time that actually works for road trips. The prediction was not just about cars. It was about showing people what a practical electric vehicle could be. That showed other companies and governments that this was not a niche. Sales grew. In 2024, China led the market with more than 11 million electric vehicles sold. The result is a cascade. More models, better batteries, smarter grids. Critics once said you could not scale this idea. They pointed to raw materials and charging limits. Those problems did not vanish overnight. But engineers and companies found ways to improve battery chemistry and charging power and to build networks that fit daily life. So, what changed in practice is simple. People stopped accepting clunky electric cars. They wanted something that fit their life. When enough people bought in, the industry shifted. And that shift is the real prediction fulfilled. Charging networks and batteries kept being the bottleneck. Engineers attacked both at once. New chemistries cut cost and made cells safer. Companies introduced sodium-ion batteries that trade a little range for much lower cost and faster charging. That matters because cheaper batteries let more makers build affordable electric cars. At the same time, charging stations went from rare to common. Ultra-fast chargers now push power at 400 kilowatt levels at some locations. That can top a battery to 80% in a time people would accept on a road trip. Smart charging software also learned to smooth demand. That lets cars fill up when power is cheap and clean. Bidirectional charging gives cars another role. They can send energy back to a home or to the grid on a hot afternoon. That turns every parked car into a tiny backup power plant. Materials and supply chains were the next problem. People worried about lithium and rare metals. Automakers and battery firms invested in recycling and in different chemistries that use more common resources. Governments offered money for factories and for charging stations. That gave companies the confidence to build at scale. So the prediction was not a single machine. It was a series of choices. Make the car desirable, build batteries that last and charge fast. Create a network that feels as easy as filling up at a gas station. Solve materials and policy issues. Then watch consumers switch. Today, that chain is visible in the cars people choose and in the roads you drive. Charging sits on city corners. Models come in every size. Energy systems talk to cars. What once sounded impossible now feels ordinary. Bezos's e-commerce revolution. You clicked buy without leaving the couch. That was the idea. He started with books in the 1990s and kept asking a single question. How do you make shopping easier than walking into a store? Bezos bet that people would choose convenience over habit. He pushed cheap prices and fast delivery, and he built the systems that made both possible. Here is what changed. Recommendation engines learned your tastes and suggested things you did not know you wanted. One-click checkout turned browsing into purchase. Fulfillment centers and careful logistics cut delivery from days to hours. Prime wrapped free shipping into a membership that made buying feel like a perk instead of a chore. He also saw that selling online was not just stores on a screen. It needed cloud infrastructure. So Amazon built services that other companies used to scale. That choice made it easier for small sellers to reach millions and for big retailers to move fast. Voice assistants and smart speakers moved shopping into conversation. Customers now reorder or ask for product ideas with a single spoken sentence. Augmented reality lets people try shoes or see a lamp in their living room before they buy. AI personalizes homepages and email offers, so shopping feels built for you. Critics warned that customers would cling to physical stores. They were wrong about the scale and right about experience. Stores still matter where touch matters. But most routine buying moved online because it became cheaper and faster and smarter. The prediction that e-commerce would dominate was not a single forecast. It was a plan. Build the technology. Solve delivery. Make buying effortless. Create the marketplace for everyone. Today, that engine runs in the background of many purchases, and it shapes how companies sell and how people shop. It all came down to logistics and trust. Amazon made buying feel instant by solving problems most stores never had to solve. The first trick was personalization. Algorithms watched what you clicked and what you ignored. Then they suggested things that fit your life. That made discovery faster and turned casual browsing into a purchase. The second trick was delivery. Huge warehouses stocked items close to where people lived. Robots and software moved boxes in the background. The promise was simple. Order tonight and get it fast tomorrow or even the same day. That convenience trained people to expect speed. The third trick was opening up the tools. The cloud system Amazon built to run its own site became a product that other companies could rent. That allowed startups and retailers to scale without massive upfront costs. Suddenly, small sellers could reach millions, just like the big brands. New frontiers kept showing up. Voice shopping moved buying into conversation. People reorder with a single sentence. Augmented reality let customers see a product in their home before paying. AI learned patterns and behavior that let stores predict needs before shoppers knew them. All of those advances built on the core idea that shopping should be easier than walking into a store. There were costs. Local shops felt the squeeze. Regulators started asking hard questions about market power. Still, the prediction proved true because the system solved practical friction points. People chose convenience and the technology followed. Gates's personal computer vision. You opened a Word document today, or you used a spreadsheet, and did not think about who made that possible. Back in the 1970s, he said personal computers would be on every desk and in every home. That sounded bold then. It also narrowed the question. How do you make a machine easy enough and useful enough that ordinary people want one? The answer was software. Gates believed the platform mattered more than the box. He and his company wrote the programs people used every day. They sold tools that let schools, offices, and small businesses do work faster. When an early computer used MS, DOS, and then Windows, it meant software worked the same way across many machines. That standard removed friction. It let developers build programs that ran for millions of users. Part of the strategy was a deal-making approach. Microsoft licensed software to hardware makers. That meant you could buy a machine from many companies and still run the same apps. It turned software into the common language of computing. Office software became the reason to buy a computer for many people. Suddenly, a machine was not a hobby toy, it was a work tool. Critics argued that Gates was creating a monopoly. They warned that one company controlling standards could stifle innovation. Those fights played out in courtrooms and in boardrooms. Yet the practical effect was obvious. Companies and homes adopted the PC because the tools made everyday tasks easier, and because the ecosystem around those tools grew quickly. So the prediction came true through a simple logic. Make computers useful. Make the software standard. Give people reasons to buy. The legal fights changed everything. Courts in the United States questioned whether one company controlling a platform could stop others from competing. That led to long trials and to rules that forced new choices. The consequence was not just a fine. It was a shift in how software companies thought about standards and about openness. Meanwhile, developers found a gold rush. Once software ran on a common platform millions of people used, building apps became a reliable business. Small teams could sell to large audiences. That created whole industries around productivity tools, games, and later the Internet-era services. Schools bought low-cost machines and taught a generation how to use them. Offices replaced typewriters and filing cabinets with software that saved time and let people do new kinds of work. Then, a surprising twist arrived. The prediction about personal machines did not stop with desktop boxes. The same idea of a standard platform turned into new forms of computing. Servers in data centers began running the same kinds of software logic. Later, the web and mobile phones carried those programs to people in new ways. The core lesson held: software that made tasks easier created demand for hardware and for networks. That cycle repeated across different devices and over time. So the prediction came true, but also evolved. It created convenience and huge economic change. It raised questions about power and about how to balance innovation with fairness. It created new businesses and new regulations. Most importantly, it changed what people expect from their tools. You now assume a machine can edit a document or sort a budget or connect you to someone around the world. That expectation began with a simple claim: personal computers would be everywhere. And from that claim came a world that never looks back. Page's search engine breakthrough. You typed a question, and the answer arrived in a fraction of a second, like a small miracle. The idea behind that speed was simple and also clever. The founders wanted to rank pages by their importance, so the best answers rose to the top. Instead of just matching words, the system treated links like votes. Pages linked by many other pages were treated as more important. That gave search results a quality filter. It meant someone could ask a vague question and still get useful answers. Engineers built crawlers that read the web like librarians and indexers. Then ranking formulas turned that index into a sorted list that felt reliable. The prediction was not only technical, it was social. Make finding information easy, and people will prefer that path. To scale the idea, the company built huge data centers and fast networks. It paired relevance with simple interfaces, so search felt instant and easy. Then a business model arrived. Ads tied to queries paid for the infrastructure and funded research that kept results improving. Over time, the core idea evolved. Semantic search and natural language models let systems understand intent instead of words alone. Retrieval-augmented generation combines stored facts with generative text to answer more complex questions. That means search is now not only about links, but about synthesizing knowledge from many sources. There were costs. Concentration of influence raised debates about bias and about who controls what people see. Regulators and rivals pushed back. Still, the practical outcome is visible every day. When you look something up, the odds are strong you will get a quick, useful answer. That outcome proves the original forecast worked, and it set the stage for a new question about how information is shaped and who decides the shape. The deeper shift was not just faster answers. It was giving machines the ability to pull facts together and tell a story. Retrieval-augmented generation lets systems search documents and then write a clear reply. That makes search feel less like a list and more like a helpful expert. For users, that is powerful. For engineers, it is a new challenge. Now, accuracy depends on the sources the system retrieves and on how it stitches them together. That opened a new set of problems. When a machine invents an answer from mixed sources, it can sound confident, even when it is wrong. That forced companies to build checks. Engineers add traceability, so an answer can show where the facts came from. They tune models to prefer reliable sources. Regulators and researchers asked hard questions about bias and about who decides what counts as reliable. Those debates matter because search shapes what millions of people believe. At the same time, search became a platform for other services. Maps, shopping, news, and voice assistants all plugged into the same engine. That made the search company more than a finder of pages. It became a gatekeeper and a launchpad. Advertisers paid to appear where intent is highest. That money paid for the massive infrastructure that keeps everything fast and evolving. The big prediction worked because it solved a real friction. People want useful answers fast. The founders showed that a good ranking system and large-scale engineering could do that. The result is a world where asking a question is often the first step in learning or buying or deciding. But the evolution continues. Semantic search, generative models, and retrieval systems are turning search into an active partner. That brings power and responsibility together in a way that will define how knowledge flows in the years ahead. Zuckerberg's social network dominance. You scrolled your feed today and felt the pull. That pull was by design. The prediction was simple. Social networks would become a primary way people communicate and share news and ideas. The platform started as a place to connect friends. The real change came when engineers turned those connections into a system that predicts what will keep you looking. The trick was the algorithm. Instead of showing everything in time order, the system learns what you click and what you skip. It then ranks posts, so the most engaging content rises. That creates a feedback loop. The more people post, the more data the algorithm gets, and the better it becomes at showing things you will react to. Network effects then lock it in. A platform with many users is more useful to each new user. That made growth explosive. Then the business model arrived. Ads targeted to interests paid for the operation. Advertisers could reach people while they were thinking about a topic. That turned attention into revenue and funded massive investment in features and in immersive tech. Virtual reality and augmented reality became the next frontier. Bets were placed on metaverse-style experiences and on building new places for social life online. There were consequences. Algorithms amplify what gets reaction, which can drive polarization and the spread of false information. Regulators and researchers raised questions about privacy and about how feeds shape beliefs. Still, the practical outcome is clear. For billions of people, social platforms are now a primary public square and a core way news travels. The algorithms kept getting smarter, and the stakes kept getting higher. Early on, the platform learned who your friends were and what made you laugh or react. Later, it learned which stories would spread and which would die quietly. That made the platform feel personal and effortless. It also made it a powerful amplifier. Power became visible in politics and in social movements. Posts that triggered emotion spread faster than calm facts. That meant outrage traveled quickly and could change public conversation in a matter of hours. Researchers and journalists noticed patterns where coordinated accounts and misleading posts reached many people before checks could catch them. That forced platforms to build moderation systems and to hire thousands of reviewers and engineers to stop the worst abuse. Privacy became another battleground. The data needed to target ads and to personalize feeds was also the data people valued most. Regulators pushed for clearer rules. Users pushed back with concerns about tracking and about how their attention was being sold. The company responded with new controls and by promising more transparency. Those promises kept evolving as new problems appeared. At the same time, the company kept innovating. It used its reach to build commerce features that let businesses sell directly inside the app. It invested in immersive hardware and software that aimed to blend the real and the virtual. That is the long game. If social life moves into augmented spaces, then the company that already knows how people connect has a big advantage. So the prediction came true in a brutal and obvious way. Social networks became central to how billions share news and keep in touch. They changed culture, commerce, and politics. They created new opportunities and new risks. The platform proved that shaping attention shapes the world. That lesson will matter for every technology that follows. Buffett's tech investment shift. You probably think of him as the cautious investor who avoided tech for years. That image misses the prediction he quietly made. He said that technology would not be a fad. The right tech companies could build lasting advantages that act like moats around a business. He proved it by changing his tune and his portfolio. The firm bought a stake in Apple in 2016. That was not a short-term trade. It became one of the firm's largest holdings and one of its most profitable bets. What Buffett saw was simple. If a product becomes central to how people live and work, then the business behind it can earn steady returns for decades. Here is why that mattered. Technology is not just gadgets. It is platforms that lock in users. It is software that makes entire industries more efficient. It is data and network effects that get stronger as more people join. Buffett understood that those forces could create long-term value, the way factories and brands used to create value a century ago. Critics said tech companies move too fast and that leaders change overnight. They warned that valuations were frothy and that a single mistake could wipe out value. Buffett conceded those risks. He stuck to companies with clear cash flow and with management he trusted. That discipline turned a prediction into a profitable play. The broader truth is bigger than a single stock. Heavy investment in technology by big firms and by markets has driven productivity in farms and factories and in services. Research labs and engineers turned bold ideas into tools that businesses rely on. The shift remade industries that seemed stable. So Buffett did not invent the technology. He predicted its economic primacy, and then acted when the evidence matched his criteria. His move showed a lesson for investors and for society. Technology matters when it solves real problems, and when it earns real profits over time. The broader effect went beyond a single stock. Big money moving into technology changed where engineers worked and where research dollars flowed. Companies with deep pockets funded long-term projects that small firms could not afford. That meant more labs and more engineers tackling hard problems. It also meant a faster path from discovery to product. Buffett saw a pattern. When a technology becomes part of daily life, it creates stable cash flows. That makes it investable in the same way a utility or a brand once was. It also changes strategy. Companies that once chased quarterly growth began buying stakes in platforms and services that promised slow, steady returns. That shifted markets and sent signals to other investors. There were costs to that shift. Concentrated investment can drive up prices for a small set of firms. It can squeeze smaller competitors. It can also steer public policy towards supporting certain technologies over others. Those are political choices as much as economic outcomes. Buffett understood the trade-off. He picked firms with clear value, and he stayed long when the business model fit his criteria. The final proof of his prediction is not in a chart. It is in how industries reorganized. Retail, media, health, and finance all adopted digital tools at speed. New firms rose to dominate supply chains and platforms. Old firms either adapted or faded. Jobs changed. Skills mattered more. That created winners and losers and shaped economic debate. So the prediction was modest and powerful. Technology would not be a fad. It would be a new kind of economic engine. Buffett bet on durable business models inside that engine, and he was right. The lesson for anyone watching is simple. Look for technologies that solve practical problems and that create repeatable value. When those things line up, markets follow. Huang's GPU AI revolution. You fed an image prompt or asked a model to write, and it answered in seconds. That speed feels like magic. The real trick is hardware built to do lots of math at once. Before this change, people trained AI on general-purpose chips. Those chips were fine for many tasks, but slow and costly for the huge models researchers wanted. The bet was that specialized processors designed to move many small calculations in parallel would make AI practical. That led to a focus on graphics processing units as AI engines. GPUs were originally built to render images. Engineers discovered the same architecture is perfect for the matrix math that powers deep learning. Companies then turned that insight into new architectures and chips that pushed performance and efficiency hard. New microarchitectures increased raw compute and added features to handle low-precision math well. That let teams train vast models in a fraction of the time it used to take. Systems could fit larger networks, and they could run inference fast enough for apps people use every day. The prediction proved out in industry moves. Data centers filled with GPU clusters. Cloud providers offered GPU servers as a standard product. Hardware roadmaps promised ever faster chips and new families designed specifically for AI. Competitors and startups built different approaches, but the core story stayed the same. Specialized hardware unlocked a wave of capability. There are trade-offs. Powerful chips require lots of energy and create new supply chain pressures. They also concentrate power in firms that can afford massive infrastructure. Still, the practical outcome is clear. What once was research grade became a platform for everyday tools. That outcome reshaped how software is built and how companies invest in AI. The pace of hardware innovation kept accelerating, and the consequences reached far beyond faster models. New chips like Blackwell raised raw speed and efficiency. Rubin promised another jump. That meant researchers could train larger models in a week instead of a month. It meant startups could prototype things that would have been impossible before. Cloud providers noticed quickly. They stocked their data centers with GPU clusters and then offered access by the hour. That changed the business model. You no longer needed a private supercomputer to build advanced AI. Teams could rent power from the cloud and spin up experiments overnight. That lowered the barrier for new ideas and let small companies challenge bigger players. But power and concentration came bundled with capability. Advanced chips need advanced factories. A few foundries in the world build the most advanced nodes. That created supply chain risk and geopolitical tension. It also concentrated advantage in companies that could afford massive infrastructure. Energy use rose, and so did scrutiny. Engineers hunted for new efficiency tricks. Companies invested in recycling and in software that squeezes more performance from each watt. Another shift was the software stack. Hardware makers built ecosystems. Libraries and compilers tuned models to the chips. That made performance gains multiply. Hardware improvements unlocked new algorithms and new product ideas. Voice assistants, image tools. And real-time translation moved from novelty to routine. The prediction that GPUs would be central to AI worked because it solved a simple problem. Researchers needed faster math, and GPUs did that best. Once the hardware existed, the whole industry reorganized. Data centers changed. Cloud services adapted. New startups emerged. The world began to use AI in ways most people did not notice, but could not live without. Jobs' touch interface future. You tap a bright icon, and the whole device answers. That simple act is the legacy of a prediction about touch that sounded unlikely at first. He pushed a world where glass served as the main way we interact with machines. Back then, most computers needed keyboards or a stylus. Apple chose a different path. It made touch feel direct and fast. The interface used gestures you could learn in seconds. That changed design thinking. Software became about fingers and faces instead of lights and menus. App stores followed, and developers built new kinds of programs that only worked with touch. The prediction mattered because it solved a real human problem. People wanted machines that fit in a pocket and that behaved like simple tools. Touch made phones feel like toys and then like lifelines. It turned cameras and maps and music into one device you carried everywhere. The result was not just new gadgets, it was a new expectation. People stopped buying devices that forced them to learn complicated controls. Hardware and software advanced together. Screens became more responsive and more power efficient. New display techniques made images clear in sunlight. Engineers built sensors that register many fingers at once, and that track pressure and motion. That pushed new user experiences and new app ideas. Even laptops are bending toward touchable surfaces. Apple is reportedly preparing a touchscreen MacBook Pro for 2026. That step would blur the line between tablet and laptop, in a way that the first phones already blurred a decade earlier. There were critics who said touch would never replace precise tools for long tasks. For many tasks, that remains true, yet touch won where convenience and immediacy mattered most. The prediction worked because it matched human habits. People wanted to reach out and manipulate what they saw. The industry followed, and the world learned to expect it. Cook's wearable health future. You glanced at your wrist and got a health alert before you even noticed anything was wrong. That simple moment is what Tim Cook predicted when he pushed Apple into wearables. He saw a future where tiny devices could quietly monitor your body and save lives. The Apple Watch started as a notification device. It became a health tool when engineers added sensors that read pulse and rhythm and oxygen levels. The device can detect irregular heartbeats and offer an electrocardiogram that doctors take seriously. Regulators in some places cleared those features after trials showed they worked well enough for screening. That changed everything. A gadget moved from convenience to real medical value. Engineers faced big hurdles. Batteries need to last a day or more. Sensors must be accurate on different skin tones and during movement. Software must filter noise so the watch does not cry wolf every hour. Apple solved some of those problems by pairing hardware with machine learning that learns your patterns. It also built privacy guards so health data stays encrypted and under your control. The market responded. People bought watches for fitness and stayed for the health features. Insurers and clinics began pilot programs that use wearable data to catch problems earlier. Researchers now run studies at scale because millions wear devices every day. That gives science a new kind of data set that was impossible a generation ago. Still, challenges remain. Continuous glucose monitoring for most people is not solved. Battery life limits constant sensing. And regulators will keep asking for proof that these tools do more good than harm. But the trajectory is clear. Wearables moved from novelty to medical device to everyday habit. They changed how we think about prevention and about when to call a doctor. He bet that tiny computers on your wrist would do more than show notifications. He pushed the company to make a device that people could wear all day and trust with their health. That bet changed how engineers thought about size and privacy and reliability. The early models tracked steps and heart rate. Then, sensors improved. Optical sensors read pulse more accurately. Algorithms learned to separate motion from real signals. Apple added an electrocardiogram feature that could flag certain heart rhythms. Regulators in some countries gave formal approval after studies showed the feature could screen people who needed care. That moved the device into a different category. It was no longer just a convenience. It became a tool doctors could use to help decide who needed attention. Building that trust required more than hardware. Software had to avoid false alarms and to let users see clear, simple results. Apple invested in privacy and encryption, so health data did not become an advertising asset. The company also worked with hospitals and universities to run studies where millions of volunteers could share data in a controlled way. Those partnerships turned everyday wearables into massive public research platforms. The market followed. Users bought watches for exercise and kept them for the health features. Insurance programs and clinics started pilot projects that used continuous monitoring to prevent hospital visits. Device makers expanded sensors and looked at non-invasive ways to read glucose and other markers. Battery life and sensor accuracy stayed as engineering problems, but progress kept coming. Still, limitations remain. Continuous glucose monitoring at scale is not solved for most people. Regulations vary by country and validation needs are high, but the prediction proved true in a quiet way. Wearables moved from novelty to medical relevance. They changed expectations about prevention and about what a small device on your wrist can do. The promise of wearables is simple and stubborn. Tiny sensors, worn every day, can spot trouble early and nudge people toward healthier choices. That promise is already working in some quiet ways. Clinics use watch data to find irregular heart rhythms before a patient even feels symptoms. Researchers use aggregated signals from volunteers to study sleep and activity at scales previously impossible. Insurers try pilots that reward steady activity. Those are small wins that add up. But scaling that promise into reliable medicine is hard. Sensors must work on different skin tones and during real life, not just in a lab. Batteries must last long enough that people do not stop wearing the device. Algorithms must avoid false alarms that waste doctors' time. Regulators ask for evidence that a feature actually improves outcomes. Those hurdles mean progress is steady and cautious rather than overnight and dramatic. What changed is expectation. People now accept that a wrist device can do more than tell time. That acceptance unlocked investment and partnerships. Tech companies work with hospitals and universities. Health systems test programs that use wearable alerts to reduce emergency visits. That creates a feedback loop. The more valid data the system has, the more doctors trust it, and the more insurance and research money flows in. The next big steps are not purely technical. They are about trust and standards. We need shared rules for data privacy and for clinical validation, so wearables can fit into care without becoming a privacy or liability nightmare. We need better integrative systems, so a doctor can see wearable data in an electronic record and act on it quickly. So the prediction played out not as a single invention, but as a long shift. A gadget became a medical tool because engineers, regulators, doctors, and users all moved together. It changed how we think about prevention and what a small device on your wrist can do. Ellison's cloud computing vision. You remember a time when companies bought huge servers and hired teams to keep them humming. The prediction was that one day those servers would live somewhere else, and companies would rent them by the hour. Ellison pushed loudly and often for that shift. The idea is simple and powerful. Instead of owning hardware, you lease computing power and storage. That frees companies to try new things without large upfront costs. It also makes scaling easy. When a site needs more capacity, you turn it up. When the traffic drops, you turn it down. That flexibility changed how businesses build software. Cloud computing grew in layers. The first layer was virtual servers that replaced physical machines. Then came managed databases, messaging services, and tools for developers. Those tools let teams focus on features, not on maintenance. Companies could deploy global services with a few clicks. That sped innovation and lowered the cost of failure. Security and compliance used to be an excuse against the move to cloud. Cloud providers invested heavily to meet those concerns. They built encryption and identity controls and multiple redundancy zones. That made the cloud safer and more reliable than many on-premise setups. Businesses that once feared handing over data began to trust the model. Another change was economics. The cloud turned capital spending into operating spending. That allowed startups to launch with little cash. It let big firms test new markets quickly. It also shifted where value sits. Infrastructure became a service, and the companies that offered it grew large because they could spread costs across many customers. The prediction worked because it solved practical problems. It made computing elastic. It lowered bar for innovation. It created new service layers that developers use every day. The real consequence is not just cost savings. It is a different way to think about building systems and about who owns what in the digital economy. The cloud did more than move servers. It rewired how companies think about technology. Once infrastructure became a service, teams could focus on products, not plumbing. That allowed a flood of new startups and experiments that would never have been possible when each idea needed its own data center. New patterns emerged. Edge computing put some processing near sensors, so latency fell and devices felt instant. Serverless platforms let developers run code without thinking about machines at all. Cloud providers added specialized chips and managed AI services so teams could try machine learning without building their own clusters. Quantum tools appeared in the cloud too, giving researchers early access without huge capital outlays. Those advances came with costs and questions. Vendor lock-in grew real. Moving data between providers can be hard and expensive. Regulators raised issues about data sovereignty and about how much control a few firms should have over critical infrastructure. Energy use and the footprint of data centers attracted scrutiny. Engineers answered by building more efficient chips, by moving workloads to cleaner grids, and by designing software that uses less energy. The business impact is clear. Companies that once needed large capital now rent scale. Small teams can compete with incumbents because they can tap the same platforms. Governments and hospitals can access powerful computing without buying hardware. Science labs can train large models and run simulations that were once reserved for the elite. Larry Ellison argued that the future of computing would be on demand. That prediction worked because it offered something practical. It lowered barriers to entry. It made innovation faster. It changed economics and governance. The cloud did not just relocate servers. It created a new economic layer that shapes which ideas get built and which companies win. So, when you next use an app that scales effortlessly or run a model in the cloud, remember this is the result of a prediction that became infrastructure and then became ordinary. That ordinary thing changed the rules.